Welcome to the deep dive. Ready to dive into some seriously cool quantum physics?
I'm ready. Let's do it.
Okay, so we got some excerpts from a physics paper. It's called Toward a Quantum Simulation of Nonlinear Sigma Models with a Topological Term.
Whoa! Catchy title.
Right, I know, but it's really fascinating stuff. Thankfully, we've got you here to help break it down.
I'm happy to help make some sense of it.
So this paper is all about using quantum computers to simulate these things called nonlinear sigma models. Can you give us a quick, what exactly is that?
It's basically like, imagine a way to understand how tiny particles interact in really complex systems. That's kind of the gist of a nonlinear sigma model.
Okay, so like a mathematical tool to understand the quantum world. Cool, but why use quantum computers? Can't regular computers handle this stuff?
That's the thing. They're not so great at it. Those nonlinear sigma models, especially when you throw in something called a topological term, way too complex. Even supercomputers struggle. So that's where quantum computers come in.
They can handle the really tough stuff.
Exactly. They use quantum mechanics, so they've got a knack for these kinds of calculations.
Like they're speaking the same language?
Yeah, something like that. It's a game changer for how we can understand these systems.
Okay, so we're talking about quantum computers being used to simulate these really complex models. But then there's this whole other thing, the mass gap. Why do some particles have mass and others don't? What's the story there?
Now you're getting to the heart of particle physics. And you're right, the mass gap is key to figuring that out. To put it simply, it determines if particles have mass or not.
So figuring out this mass gap thing could help us understand like the fundamental structure of the universe.
Precisely. It's a crucial piece of the puzzle for sure.
Wow. And this paper suggests that these quantum simulations could actually help us do that.
Yeah. It's pretty amazing, right? They're using a fascinating concept, too. Entanglement entropy.
Entanglement. Now that's a word that always sends shivers down my spine. It's like the spooky, mysterious side of quantum mechanics.
It definitely has that reputation, but it's incredibly cool. Imagine two particles linked, and even if you separate them like really far apart, knowing about one instantly tells you about the other.
Whoa, they're connected no matter what.
Exactly. As if they're communicating instantly across any distance. That's entanglement.
So if we could understand this entanglement language, we could unlock so many secrets.
You got it. And in this paper, they're saying that by measuring the entanglement entropy, we can actually see if a system has a mass gap or not.
So entanglement is like this secret code, and if we crack it, we can learn so much more. Man, this is already blowing my mind. It's like these particles are having these secret conversations, and we're just starting to eavesdrop. But this research goes even deeper, right? I mean, the paper mentions strong coupling and weak coupling. What's that all about?
You're right, there's more to uncover. It's kind of like, imagine how particles interact. In strong coupling, they're constantly chatting, really influencing each other. But with weak coupling, it's more like a nod in the hallway. They're aware of each other, but not deeply connected.
So it's like the difference between, say, a heart-to-heart with your best friend versus just making eye contact with someone on the street.
Exactly. And these different levels of interaction, they actually impact the mass gap.
Really? How so?
Well, think of it this way. In the strong coupling regime, the mass gap is super clear. It's like a loud, booming voice. But in the weak coupling regime, it's subtler, like a whisper that's easily missed.
Okay, so the strength of their interactions changes how noticeable the mass gap is. Fascinating.
So,
Where do quantum computers fit into all of this compared to our everyday computers? Who's winning this quantum showdown?
it's a good question. And the research actually compares how well each type of computer handles simulating this nonlinear sigma model.
Yeah.
Turns out quantum computers have an edge, especially in the strong coupling regime. They're much better at representing the system.
That makes sense. They're kind of built for this quantum stuff. But you said especially in the strong coupling regime, does that mean there are times when our regular computers still hold their own?
Yeah, that's the thing about quantum computers. They're still in their early stages. They have limitations. The paper talks about Hamiltonian truncation, basically. We have to simplify the models for the quantum computers to handle them. And in the weak coupling regime, that simplification impacts the accuracy.
So it's like we're giving them an incomplete picture.
Exactly. And it turns out that for now, conventional methods, especially something called tensor networks, actually work better for the weak coupling regime.
Tensor networks. That sounds intense. What are those?
It's kind of hard to visualize, but imagine a way to map out all the complex relationships between entangled particles. That's essentially what a tensor network does. It helps us organize and understand the massive amounts of information involved in these systems.
So it's like a map of the quantum world. That's amazing. I love how this isn't just about one type of computer winning. It's about using the best tools for the job, whether they're quantum or classical.
I agree. It's a really exciting time to be exploring these questions and seeing how different approaches can work together to help us understand the universe.
It really is. And it sounds like we're on the verge of some major breakthroughs. This is way bigger than just a competition between computers, though, right? It's about what we can actually learn about the universe.
Absolutely. And while this paper zooms in on particle physics, its implications could shake things up in other fields too.
Like, what else could these quantum simulations do? Give me some examples.
Okay, so imagine creating materials that are like lighter than ever, but also way stronger. Or what about simulating how molecules work in our bodies to design super targeted medications?
Wait, are you talking about, like, revolutionizing space travel or finding cures for diseases that seem impossible to treat right now?
It sounds crazy, but yeah, that's the potential we're talking about. This research is a huge leap forward in using quantum mechanics to tackle some of the biggest questions out there.
I gotta say, at the start of this deep dive, I thought we were just dipping our toes into some seriously complicated stuff. But now it's like we've traveled through the quantum realm.
Yeah.
Entangled particles, the power of quantum simulations.
It's a wild ride for sure. And we're just getting started, which is so exciting. There's so much more to find out. And I think we're on the brink of some serious breakthroughs.
My brain's definitely buzzing. It's amazing to think that by exploring this weird and wonderful world of quantum physics, we might actually solve some huge problems for humanity.
Right. It shows that even when things seem impossible, curiosity and scientific exploration can lead the way.
So true. And on that note, we're wrapping up this deep dive into the quantum realm. We've explored the mass gap, the potential of quantum simulations, and so much more. If you're as mind blown by all this as I am, check out the full paper. There's a link in the show notes. Until next time, keep those brains buzzing.